Hey guys, all right, so we're on 4.2, the mean value theorem, okay? The mean value theorem is another existence theorem like the intermediate value theorem, which we will be referring to in this also. Okay, the intermediate value theorem stating that if you have a point, oh, I need to be able to draw on here. How do I do that? Oh yeah, right here. Oh, there it goes. Okay, so if you have a point A and a point B, and there's some continuous function, and it goes through this line, if you know that point A is below the line and point B is above the line, then it will cross the line since it is a continuous function. That's the intermediate value theorem. Okay, so we are going to be referring to that. So the mean value theorem is if f is continuous on the closed interval from A to B, and differentiable on the open interval from A to B, then there exists a number C in the interval A to B such that f prime of C equals f of B minus f of A over B minus A. And that should look very familiar because this is, I want to change colors, this is the formula for the rate of change. The average rate of change. We use that in chapter 2. Okay? All right, so we have that. I'm going to scroll down here. Oh, I wish it would stay. How can I get it to stay? Oh, whatever. I'm going to clear the work that I have there. Clear ink. So we have this graph, and we have a continuous function pictured on this graph, just a little bit of a curve. And let's put that we have A over here, B over here, and we'll let this point represent some value, x value C. Okay? Well, we know that this function is continuous from A to B. And it is differentiable from A to B because we can see the graph, we can see it's continuous, we can see that there's no corners, cusps, jumps, breaks, gaps, nothing. There's nothing that would make it not continuous, so it is differentiable on this also. So remember, when we're looking for differentiability, we're looking for being able to take the derivative, so finding the slope of the tangent line at that point to the curve, okay? So this would be considered continuous on the interval, the closed interval A to B, and differentiable on the interval A to B, the open interval A to B. So that means that we can assume that all points in between, since it's continuous and differentiable everywhere, then we can assume that at every point it's going to be differentiable, okay? So then all values in between are differentiable. Okay? Now, the mean value theorem has to do with the endpoints. So when we're looking at endpoints, we're looking at, from one end to the other, exactly what I mean when I said endpoints, right? And when we average that out, that's what that formula is. Pretend that these are parallel. That rate, that slope, should be equal to the slope of the tangent line at that same C value, as long as the function is continuous and differentiable. That'll work. So that's where the mean value theorem comes into play. Okay? So I'm going to clear that. So it won't let me scroll down and move it with it. Okay. So now here are some conceptual questions. This is a real life question, right? So if you average 55 miles per hour on a trip, does that mean at one point in time you drove 55 miles per hour? Well, think about it. If you're driving your foot's on that gas pedal, you're increasing in speed, you might be slowing down for a bump, so you decrease, you increase, it's continuous. Driving is a continuous function, okay? There's no jumps, holes, gaps, or breaks, none of that, okay? Unless you crash, right? No, I'm just kidding. But, yeah, okay. Anyways, so, yeah, at one point in time, you would have driven 55 miles per hour. If your average is 55 miles per hour, that means you must have been at 55 miles per hour at some point during that trip. So the answer is yes, because you can't skip speeds. You can't go 50 miles per hour and then go 60 miles per hour and then be like, oh, my average must be 55. No, you can't just skip speeds. You either increase up to that point and then decrease down. So you will reach it at some point. There's no breaks in this graph. It is continuous. I'm missing the dot for the I. Okay. So looking at the graph, it says if f is continuous on the closed interval from A to B, and there's supposed to be a line right here. I don't know why it doesn't show up. Okay. Is this going to be applied with the MVT, the mean value theorem? Well, we know that the mean value theorem says if f is continuous on the closed interval from A to B and differentiable on the open interval from A to B, then there exists a number C in the interval such that f prime of C equals that average rate of change formula. Well, this is a closed interval from A to B, but is this function continuous? You can tell right now that it's not. It's got to jump, so it's not continuous, okay? So because it's not continuous, Lucas and Violet, please stop. Since it's not continuous on the closed interval from A to B, actually closed A to B interval, that means that the MVT can't apply here. I can't apply the MVT, the mean value theorem, to a function that is not continuous. So MVT, the mean value theorem, does not apply. It's important for us to know when we can apply it and when we can't. Because if we can't, then it makes the problem really easy. You could be like, oh, it's not continuous. That means it's not differentiable. So that means that the MVT doesn't apply. Boom, done. So those are pretty easy. Okay? All right, so on to the next one. I got to clear the ink. If Joe scored an average mean of 12 points per game, does that mean there exists a game in which Joe scored 12 points? What part of the mean value theorem does this violate? Well, is this continuous? You score like 11 points in one game and 13 points in another game, and is that, when you find the average, yeah, the mean will be 12, but is that continuous? It's not. It's not like you're driving and you're increasing speed to get to that level and then back down. You can't do that. You have to stop and start a new game. And so because of that stop, there's a break in the graph. And so it won't be continuous. So we can say, no, he could score 11 points and then 13. This is not, oops, I can spell. I can erase, but this is not continuous.
That is
on a closed interval. Okay. All right. And differentiable at every point of its interior from A to B. So if it's not continuous, the MVT doesn't apply, and it also needs to be differentiable for the MVT to apply. So absolute value is like an automatic no-no. And why is that, you ask? Because of what? Can someone say to the camera what that is? I know I can't hear you, but maybe I can feel the vibe. I don't know. This is a what? It's a corner. And we know that at a corner, it's not differentiable. So it's not differentiable. It is continuous, but not differentiable. So that means that the MVT does not apply. Much better if I fill it in. Oh, it's kind of fun. Satisfying. All right. And let's add here corner. So not differentiable. Okay. All right. So there's that part. I'm gonna keep scrolling. Just keep scrolling, scrolling, scrolling. On to the next page. And we have x squared plus y squared equals 1. That's a circle, but on the graph we only see the top half of this circle. And the first question is, why isn't the graph differentiable at x equals -1 or x equals 1? Okay, well, look at the graph. At x equals 1 and x equals -1, it's not differentiable because what do we have here? Look at these tangents. What kind of lines are those? We've got some vertical lines, right? So we know that we can't, that's another point where it's not differentiable when we have vertical lines because the slope of a vertical line is undefined. So we have vertical tangents. That is why the graph is not differentiable at x equals -1 or 1. So is there a point C for which f prime of C equals f of B minus f of A over B minus A? Well, let's see. We know our interval has to be from -1 to +1. Okay, so I have the points -1, 0 and +1, 0. Okay, so let's see if we can find f of C. Well, we have f of 1 minus f of -1 all over 1 minus -1, using that formula. Okay, well, f of 1 is 0. F of -1 is also 0 over 1 plus 1, which is, 2. Well, 0 divided by anything is 0. So that means that f prime of C equals 0. Okay, well, if f prime of C equals 0, isn't that where the slope of the tangent line is equal to 0? Well, the slope is 0 right here. Because we have a horizontal tangent there. So that means, yes, there is a point, and it's at the point, what point is that, 0, 1? And there we go. So that means that the C value was, the x value is 0. So f prime of C is 0 at x equals 0. So let's also put so C equals 0. Let me put that in a different color. Okay. All right, so I'm going to scroll. So I got to clear the ink. Scroll and scroll and, whoops, too much. State whether or not the function satisfies the hypotheses of the mean value theorem on the given interval. If it does, find each value C in the interval from A to B that satisfies the equation f prime of C equals f of B minus f of A over B minus A. So the hypothesis of the mean value theorem is that if a function is continuous and differentiable, then there should be this, okay? So the hypothesis is the if part, and the conclusion is the then part. So I'm looking at the hypothesis, and I need to see if this is continuous and differentiable. So it really helps to start with graphing it. It's something simple. The square root of x squared plus 1, we can totally graph that. Not a problem. Do you guys like my hat, by the way? I got it at Tahoe, Lake Tahoe. I was very happy. I found it at a gas station, and it's pink with camo. I'm like, perfect. So, anyways. All right, so this interval is from -2 to +2. Okay. Let's see. All right, so if I plug in a -2 to start off my interval, -2 squared is 4. The square root of 4 is 2. 2 plus 1 is 3. So -2, 3. I'll use a different color. Okay. If I plug in, the next number would be a -1. -1 squared is 1. The square root of 1 is 1. 1 plus 1 is 2. If I plug in a 0, 0 squared is 0. Square root of 0 is 0. 0 plus 1 is 1. So 0, 1. If I plug in a 1, we know the square root of 1 is 1. 1 plus 1 is 2. And then we can kind of figure out that it's mirror imaging. So this is really an absolute value in disguise. Okay, so does the MVT even apply to this? Look at that picture. What about it is making the MVT not apply? I'm gonna use a different color. That is. What is that? Well, it's a corner. And corners make it not differentiable. So it's continuous, but it's not differentiable. So this is how we're going to write this up. We're going to say f of x does not satisfy the MVT on the interval -2 to 2 because it is not differentiable at the corner x equals 0. Is x equals 0 at that corner? That's my write-up. Okay. It's important to get these write-ups down, guys. I know on the homework we're not being a huge stickler on these, but on quizzes and tests we are. So you lose a lot of points on those FRQs if you don't have a write-up going on. Got to make sure that you do that on the AP test. It's huge. So you got to be able to justify your answer in words mathematically. Okay. All right, so that's the first example there. So I'm going to scroll down, which means I got to clear the ink again. Next example. So this time we have f of x equals x cubed plus 3, where x is less than 1, and x squared plus 1, where x is greater than or equal to 1 on the interval from -2 to 2. And we need to see if the mean value theorem is going to apply, and if it does, what c value will satisfy the equation. So let's take a look. First of all, is this continuous is what we have to look at. So it helps to draw a graph. So let's start with the x cubed plus 3. You know what? I can change the color. Let me change the color. I want purple. Okay. And I can move that. Oh, that's so cool. Okay, anyways, sorry, got distracted. All right, so if I plug in, I have to plug in numbers that are less than 1 right here. So I can plug in -2. That's less than 1. So -2 to the third power is -8. Negative 8 plus 3 is negative 5. So negative 2, negative 5. I need to add one more down here. So negative 2, negative 5, I have a point. I'm like, where'd it go? If I plug in a negative 1 cubed is negative 1. Negative 1 plus 3 is 2. So negative 1, 2. And then at 0, I could plug in 0, that's less than 1. 0 cubed is 0, 0 plus 3 is 0, so 0, 3. Okay. And then I can't, or I can plug in a 1, but it's an open point because I can't equal the 1. So I plug in a 1, 1 cubed is 1, 1 plus 3 is 4. So 1, 4, but it's an open point there. So I know it's going down like this. Okay, it's a cubic. All right, for the next one, I really want to find a hot pink, and I don't know how to make it happen. It's gotta be in the red somewhere. Whatever. That green looks fun. We'll do that green. Okay, so, all right, I can plug in numbers greater than or equal to 1, so I'm gonna start with a 1. 1 squared is 1, 1 plus 1 is 2. So 1, 2, and it's a closed point. Plug in a 2, and then I'm at the end of my interval. 2 squared is 4, 4 plus 1 is 5. So 2, 5 would be right here. So 2, 5. And that's a parabola, so I know it curves up like that. All right, well, is this function continuous? Nah. You've got to jump. Jump, jump. So it's not continuous. So that means it's not differentiable, and it needs to be continuous and differentiable in order for the MVT to apply. So I can't do it. So I have to do the similar write-up as the last example. I'm going to say f of x does not satisfy the MVT. Go away, go away. All right. Not satisfy the MVT on the interval negative 2 to 2 because it is not continuous or differentiable this time. Last time it was continuous. It just wasn't differentiable last example. This time it's both because it's not even starting off continuous. It's not continuous or differentiable at what x value is it not? That is at an x value of 1. So at x equals 1. All right. So I'm going to clear the ink and go on to the next example. All right, f of x equals x squared on the interval from 0 to 2. Well, this is an x squared, and we know that x squared is a parabola. It's the parent function. Like, we don't even need to do much there, okay? We're looking at the interval from 0 to 2, so I'm only looking at, I wish that this eraser would work. Whatever. Oh, delayed response. Okay, delayed response, there we go. All right, so it's on the interval from 0 to 2, so we'll just put an endpoint there to 2, okay? And if that's a 2, then this y value, 2 squared is a 4, okay? So it is continuous, and it is differentiable because there's no corners, there's no breaks, there's no jumps, there's no cusps. So it is continuous and differentiable, so that means the MVT applies. Oh, so we actually get to use the MVT? Yay, okay. So that means we need to look at the derivative. So first of all, look at the derivative. So we need to find f prime of x And the derivative of x squared is a 2x. Okay? All right, now that we have that, let's apply the MVT, f prime of c equals, so on that interval it would be f of 2 minus f of 0 all over 2 minus 0. Okay? Well, if I plug in a 2 into f of x, f of 2, let's see, 2 squared is 4, so that would be 4. F of 0, plug in a 0 for the x squared there, would be 0 over 2 minus 0. So that's basically 4 over 2, so the derivative is, or the average rate of change is a 2, so slope is 2. Okay, so according to the mean value theorem, if a function is continuous and differentiable, that means when we find the average rate of change between the endpoints, it should be equal to the derivative. So we can find that c value that's going to make this true. So that's the next step. Okay, so now let's set these equal. We'll set f prime of c equal to f prime of x. We'll set those equal. So we'll have 2 equal to 2x. And so actually, yeah, and so we'll get that x equals 2. So the c value that makes this true is a c value of 2. And that's it. No need to make a write-up. We found the c value. Oh, c value is not 2. Mrs. Garcia. Two divided by 2 is 1. So the c value is 1. So if you're screaming at the computer screen at me, I'm sorry. I fixed it though. At least if I noticed it after the fact and not like after I finished the video. That would have sucked. I hate it when I do that because then I have to redo the video. Nobody wants to do that. All right, so next one, I'm going to clear the ink. If it lets me, there it goes. And scrolling, scrolling, scrolling. F of x equals the square root of 1 minus x squared on the interval from -1 to 1. Well, first of all, this graph seems pretty small and simple. Let's go ahead and graph it and see what's going on so that we know if it's continuous and differentiable right off the bat. Okay, so I'm going from -1 to 1, so it's really little. I don't know how high up I'm going to go, so we'll just have to play with it there. So for right now, let's plug in a -1 for x. -1 squared is 1. 1 minus 1 is 0. The square root of 0 is 0. So we have a point at -1, 0. Okay. If I plug in a 0 for x squared, 1 minus 0 is 1. Square root of 1 is 1. So I need 1 up there. So I'll put a 1 and a -1 to keep it balanced. Okay, so 0, it would be 1. If I plug in a positive 1 for x, 1 squared is 1, 1 minus 1 is 0, square root of 0 is 0. So I am getting this. Okay, well, there's no corners, there's no jumps, there's no gaps or breaks, so it is continuous and differentiable. So we can say f of x does satisfy MVT everywhere on this graph, everywhere from -1 to 1. Okay. So next we need to find the derivative. So let me use the formula. So we need f prime of x. All right, well, this is really 1 minus x squared to the 1/2 power because it's a square root. So we're gonna have to use chain rule on that when we take its derivative. So let's take the derivative of the inside. Derivative of 1 is 0. Derivative of -x squared would be a -2x using power rule on that. Okay, and then, why didn't you erase? Whatever, that's an x. All right, and then we have to take the derivative overall, so that 1/2 has to get dropped down, so times 1/2 times the stuff on the inside, but now the exponent is 1/2 minus 1, which is a negative 1/2. Okay, so let's clean this up a little bit. These 2's will cancel. This is gonna get dropped like it's hot, 'cause it's got that negative exponent, and we're gonna convert it back to a radical when it's down there. And this x, it's a negative x, but its exponent is positive, so it's gonna stay up top. So f prime of x equals negative x over, drop it like it's hot, the square root of 1 minus x squared. So there's our derivative, okay? The next step is to apply the MVT. So let's do that. We're finding f prime of c. Okay, so on the interval, that means we're finding f of 1 minus f of negative 1 all over 1 minus negative 1. Okay, well, f of 1 we see is 0. F of negative 1 is also 0. Over 1 plus 1 is 2. 0 divided by anything is 0. So we know that the f prime of c equals 0. Okay. The next step will be to set this equal to this, because according to the MVT, the derivative of the function, where it equals 0, should be the same as the average rate of change. So derivative and average rate of change should be the same, so we can set them equal to each other. All right, so we can say 0 equals negative x over the square root of 1 minus x squared. And if I solve for x, I would need to multiply by the square root of 1 minus x squared to both sides. And this gets wiped out, and that gets wiped out too, because 0 times anything is 0. So x equals 0. Okay, which means that c equals 0. The c value is 0. Okay, and that's pretty cool, huh? These are not so bad. Next example. Ooh, I see some trig. You guys know how I like the trig. I'm going to clear it. Scrolling, scrolling, scrolling. Tangent of x. It's been a little bit since we've done a graph on that. So we are going to need to say the same things for this function, tangent of x, on the interval from 0 to pi. And we are going to need to dig up our skills on graphing tangent, but it won't be bad. So we know what tangent looks like. It looks like this, okay? And it has asymptotes around it. That's what tangent looks like, and it repeats that through the different cycles. Well, when we are graphing it on this interval, we have to remember, well, where are the asymptotes at? Well, they were at the increments of plus or minus pi over 2. So at all the pi over 2 locations, there's an asymptote. All right, so when we graph this, we graph it in increments of pi over 2. Pi over 2, and then pi over 2 plus pi over 2 is pi, okay? And I'm going from 0 to pi, so from 0, 0 to pi, that's my closed interval, okay? And normally when we have on this graph, we usually have from 1 to negative 1, but it's tangent, so there's no height or there's no lower high. So anyways, I have a asymptote at pi over 2. I don't know why it's like that. There's my asymptote. And I know that for tangent, I'm going to have a point right at 0 and right at pi. But remember, it does the weird, like kind of like a cubic, all right? But since I can't go to the left of 0, I can't go on the negative side, it stops at 0, I can only hug the wall on the right. I can't, there technically would be a negative pi over 2 over here, and then the asymptote, and then the rest of it would be down there. But because it's out of my interval, I'm not gonna graph it. Okay, so there's that part. Same here, I would have a 3 pi over 2, and then, you know, the dashed line for the asymptote, and that would hug the wall going up, and hug the wall going down, but I can't hug the wall going up because then I'm past pi, and pi is the end point of my interval. It's only from 0 to pi. So this is the only part of the function that I am seeing. So looking at that graph, is this continuous? No, there's an asymptote. There's a break in the graph, so it is not continuous, so it's not going to satisfy the MVT. So we can say f of x does not satisfy the MVT because it is not continuous or differentiable at what x value is making it not continuous? Well, look where the asymptote is. That's a restriction. So at x equals pi over 2. There we go. I really like this next question. It has to do with something in real life. My husband's best friend is a cop, and so I even took a picture of it and I sent it to him because I'm a nerd, and he kind of is too. I used to help him with his math. He got an associate's degree so he can move up to a detective, and you need a lot of math involved for that, and for, what was it called? Major accident something or other. He would be called, like in the middle of the night if there was a major accident, somebody died, he'd be called in, and he'd have to go to work, and he'd have to measure skid marks and stuff like that to figure out how fast each car was going, who was at fault. There's a lot of math involved with that, and he had to use calculus. But they give him all the formulas, so he doesn't know he is using calculus. He just knows how to plug stuff into the formula, pretty much, which is what it is. Let me clear the ink so I can scroll. 2 stationary patrol cars equipped with radar are 5 miles apart on a highway. As a truck passes the first patrol car, its speed is clocked at 55 miles per hour. 4 minutes later, when the truck passes the second patrol car, its speed is clocked at 50 miles per hour. Prove that the truck must have exceeded the speed limit of 55 miles per hour at some time during the 4 minutes. Okay, so this is fun. All right, at the first patrol car, this car, we'll count that as at time 0. That was when he was first recording this car's speed, okay? At time 0, the car was going 55 miles per hour. And then it goes 5 miles, because they're 5 miles apart on a highway. And the second patrol car clocks his speed, and it was 4 minutes later, and he's going 50 miles per hour. Okay, and they're saying that this truck must have exceeded the speed limit of 55 miles per hour at some time. We need to prove that that happens. So let's take a look at this. Now, when we're traveling on the road, our speed limit is in miles per hour. Right now we have 0 hours at 55 miles per hour, and then 4 minutes at 50 miles per hour. So we're in different units here. We need to convert those units so that those 4 minutes need to be changed. So we need to change 4 minutes to oops, go away, to hours. Okay, so to do that, well, we have 4 minutes. We need to multiply that by 1 hour, but we need the minutes to cancel. Well, how many minutes are in an hour? 60. Okay, so then the minutes will cancel, and I get 4 over 60, which reduces to 1 over 15. So 1/15 of an hour is 4 minutes. Okay, so we're going to rewrite our points here. We're going to use 2 different endpoints. So, well, the first endpoint is the same because it's fine. So 0, 55, and then instead of 4 minutes, we're going to use 1/15 of an hour, comma 50. So we're going to use these. Because now we're in the same units. We're in hours instead of mixing hours and minutes. So you always have to be uniform. All right, so we already know, because we talked about this in the very first example, first page, that driving and getting up to speed and down and going, changing, fluctuating in our speeds when we're driving is a continuous function. Because there's no stops or breaks. Until you stop, then that trip's over. But that trip itself is a continuous function. Okay? So we're going to apply the MVT. So we're going to do the formula, f prime of c equals, I'm going to do f of 1/15. So basically the 50 minus, the y2 minus y1, because it's basically slope formula, over x2 minus x1. Okay, 50 minus 55 is -5 over 1/15. Dividing fractions, it's easy as pie. You flip the second and multiply. -5 times 15 equals -75 miles per hour. Now when we're measuring speed though, we always measure the absolute value. So the absolute value of -75 is positive 75 miles per hour. So this truck's average speed was 75 miles per hour. So that means he did exceed the speed limit of 55 miles per hour at some time during those 4 minutes. So now time for our write-up. So let me see if I have room, and I want to use a different color. I think I'm going to go purple again. Oh, I lost my purple. Oh, there it is. All right. I'm going to erase this because it's in my way. Okay. This write-up's kind of long. So we're going to say, since the truck averaged 75 miles per hour over the interval from 0 minutes to 0 hours to 1/15 of an hour, and his speed was continuous and differentiable, because we have to always say that in order to use the MVT. It's always differentiable over the open interval, so from 0 to 1/15, comma, by the mean value theorem, by the MVT, there exists. Now, instead of the word there exists, I'm going to show you a different symbol. It's a backwards capital E. There exists a point in time which is in the interval from 0 to 1/15. This symbol means the words in, so in this interval, such that, what am I trying to say? His speed was 75 miles per hour, which is over 55 miles per hour. Okay, so at some point in time, he did go over the speed limit. So if he is getting written up with a ticket, he deserves it, especially if the cop can do the math like this. Power to him. It's easy math. Anyone can do this kind of math. Okay, it's just averages. All right, so I'm going to go down to the next one. So I'm going to clear the ink. The height of a ball t seconds after it is thrown upward from a height of 32 feet with an initial velocity of 48 feet per second is f of t equals -16t squared plus 48t plus 32. Verify that f of 1 equals f of 2. Oh, that's easy. Okay. Letter A. what's f of 1? That means we plug in a 1 into the function, so we'll have negative 16 times 1 squared plus 48 times 1 plus 32. So that's negative 16 plus 48. So that's what, 32. 32 plus 32 is 64. Okay, let's check f of 2. Be negative 16 times 2 squared plus 48 times 2 plus 32. Well, 2 squared is 4. Negative 16 times 4 is a negative 64. I'm just going to put off to the side here. 48 times 2, 16, 96. Okay, so 96 minus 64 is 32. 32 plus 32 is 64. So they both are equal to each other. So check, verified it, did the work. All right. Next, I think that should change back to blue. Yep, it did. According to the mean value theorem, what must be the velocity at some time in the interval from 1 to 2? Okay, I'm going to answer it over there, but over here, let's take a look at a graph. So this function, I see a t squared, that's the highest degree, so that means that this is a parabola. It's a downward facing parabola because of that negative out front, and the y-intercept is a positive 32. So I know it's crossing through the y-axis at 32, okay? And I also know that this is from the interval from 1 to 2. And at 1, the height is 64. So let's pretend that this is 64. So we have a point at 164 and a point at 264, okay? And we know that we have a point at 0, 32 because that's its y-intercept. So it's a parabola, so it's going to come up and then back down. I don't know how high up it's going. I'm totally faking it. But we know that this is a closed interval from here to here. Closed. Okay. So technically, I'm only looking at, oh, it's actually working. From here. No! No, no. I hate it when it does this. No!
Hey, look, it's Star Wars.
Okay, I was about to freak out for a second. I was like, no. Okay.
Oh, no.
How come it'll let me erase some of it? Okay. I don't like that there's a delay. It throws me off. Okay, so it's just that little piece right there from the interval 1 to 2. Well, it's continuous. It's differentiable. There's nothing about that little curve right there that's going to make me not be able to take the derivative. There won't be any vertical tangents. There won't be any corners, cusps, or breaks. So it is continuous and differentiable. So we will be able to find the point in between 1 and 2. Okay, so that's where we're going to apply the mean value theorem. So f prime of c is going to equal f of 2 minus f of 1 all over 2 minus 1. Well, f of 2 we found is 64. F of 1 is also 64. So I have 64 minus 64 over 1, that's 0 over 1, so this is 0. Which makes sense, doesn't it? It's the slope of the tangent line. Okay, so the velocity equals 0. That's what the derivative means here. Okay, so now let's answer the part B. So we can say as our answer, since f of t is continuous and differentiable over the interval 1 to 2, and f prime of c equals 0, then, oops, instead of there exists, I was going to do it. Then there exists, it's nice when you can use the symbol to shorten it up. there exists a C value in the open interval from 1 to 2 such that the velocity at C equals 0. And this is by the MVT. All right. We have, what, 2 more examples and we're almost done. All right, so I'm going to clear the ink. Scrolling, scrolling. That's not a scroll. Can you scroll, please? There we go. Go away. Let f be continuous on a to b and differentiable on a to b if there exists c in the open interval from a to b such that f prime of c equals 0. Does it follow that f of a equals f of b? Now this one's tricky because we just did an example and f of a and f of b ended up both being 64, right? They both ended up being at the same level. Well, will that happen all the time? No. Okay. So for your notes, we'll put, it sounds like the previous example, except it's in reverse. So, but in reverse. We can't automatically assume stuff just because we notice a little bit of a pattern. It's not a pattern that's going to work for everything, okay? When f prime of c equals 0, that means that we have a horizontal tangent because the slope of a horizontal line is 0. But horizontal tangents can occur anywhere as long as the slope of the tangent line is 0. So it doesn't have to work out for f of a and f of b to be equal to each other. So f prime of c equals 0, this can happen without f of a equaling f of b. And we have to show a counterexample to show this. So for instance, say we have a curve on this interval from a to b. It's like this. So this is f of a and this is f of b. They're not at the same level, but it will have a tangent where the slope is 0. It will have a horizontal tangent to it. So this is our counterexample to disprove that statement up above. Sometimes our counterexample is in words, sometimes it's just a picture. And a picture here is good enough. All right, next question, so our next example, so I'm going to clear the ink and scroll. Okay. The figure gives 2 parts of the graph of a continuous differentiable function f on -10, 4. The derivative f prime is also continuous. Well, looking at this picture of the graph, it said it's continuous, right? Well, does that look continuous? No. But it says that it is, and it says that it's also differentiable. So that means that there's some pieces that are missing from this graph. So, oops, not on the right page. So the graph is missing pieces, okay? And in letter A, I'm not going to scroll up, so you'll have to look at it on your paper. It says, explain why f must have at least 1 0 in the interval from -10 to 4. So this is counting by 2, so this is -10. Well, a 0 means that the graph is going to cross through the x-axis. If this is continuous, to connect from here to here, there shouldn't be any gap or break, so it should eventually, since this part is below the x-axis and this part is above the x-axis, it should cross over when they do connect, however they connect, okay? So yes, it will have at least 1 0. So to say that answer for part A, we'll say since f is continuous by the intermediate value theorem. That's the one that states if you have a point B up here and a point A down here, and then there's a line, as long as there's 1 point below, 1 point above, and it's continuous, it will cross that line at some point. We don't know how many times, but it will at least cross one time. Okay, so that's the intermediate value theorem. So by the IVT, intermediate value theorem, there is at least 1 0 on the interval -10 to 4, since f of -10 is greater than 0, it's above the x-axis on that side, and f of 4 is below the x-axis, so less than 0. So maybe for your notes, put that f of -10 greater than 0 means above x-axis, and f of 4 less than 0 means below the x-axis. Man, I need some water. So my breath is kicking. All right, so there's part A. Part B, I'm not going to scroll up so you guys can see it, so I'll just read it. It says, explain why f prime, the derivative, must also have at least 1 0 in the interval -10 to 4. What are these zeros called? So for it to have, for the derivative to have a 0 on there, that means that we have to have slopes that cross over from positive to negative. Well, that will happen because if we cross this over to connect, it's going to go from a slope that's positive, or so negative, and then, it goes from slope positive to negative, okay? So it's going to happen. That's when we have those horizontal tangents. So, for instance, even if it just connected simply like that, we would have a horizontal tangent right here. So it would have at least 1 0 on the derivative graph, because that would be on the derivative graph where it crosses the x-axis at. Okay. So it will have at least 1. And I say at least 1. There could be more because it could be doing stuff like this before it connects. We don't know. So there could be more than 1, but there is definitely at least 1 because of the intermediate value theorem, because we have slopes above and slopes below that x-axis. Okay. So for part B, you can say, given f is continuous and differentiable on the interval from -10 to 4, and f prime of -10, the slope of the graph here would be a positive slope, right? So that would be greater than 0. And f prime of -4, so the slope at this portion is obviously negative, so less than 0. By the IVT, the intermediate value theorem, there exists, that symbol, a C in the interval, the open interval from -10 to 4, such that f prime of C equals 0. And we learned in the last section that those are called critical values, which are called critical values. Okay? All right. Part C says make a possible sketch of the function with 1 0 of f prime on the interval from -10 to 4. All right, so we're going to make a possible sketch, and that's going to be just like how I did it earlier, where it has 1 0. That means we need to have one spot where it curves over, and I would have a horizontal tangent. So if I do it like this, I would have a horizontal tangent there. So this represents in green, part C, where f prime has 1, 0. Okay, because that's where the slope is 0. All right. And then part D, it says, make a possible sketch of the function with 2 zeros of f prime on the interval. So for 2 zeros, I just need to have a max and a min. So what if I did it like this, where it goes and then, oh no, that'd be 1, 2, 3. Let me fix that. Pretend that's not a corner, because it's not. All right, so then I would have a horizontal here, and then I would have f prime would have 2 zeros. The slopes are 0 there on that interval. In fact, to make this a little bit better, because then that one looks like a third 0, let me do this a little bit better. Make it so it goes down and then up and then like that. And now we can see the 2 zeros. That looks better. Good job, Miss Garcia.
Yeah.
All right. So that is everything, you guys. I hope that you enjoyed this lesson. I hope you like it up on the smartboard here, and have a great day. Bye.